So I'm going to be talking about Mendelian randomization. Oh, take this off. I'm going to talk about Mendelian randomization. The bottom lines, which I'll tell you up front, are, and the takeaway messages, are this is an extremely powerful method, but it's one that is easy to, where it's easy to go wrong. So there's a lot of pitfalls, and you have to be extremely careful in doing it, or and think carefully when assessing Mendelian randomization evidence. Okay, so let me start with some intellectual history. So apparently the first appearance of Mendelian randomization in the genetic epidemiology literature is from a paper in 1986. And the issue that the author Catan was struggling with was that it was known that low cholesterol levels in the blood was associated with increased risk of cancer. The question was, how do we interpret this epidemiological association? Is it causal? Is it the fact that if we reduce someone's cholesterol levels, will increase their cancer risk? Or could it be reverse causation? Maybe in early stages of cancer, your cholesterol levels go down. Or maybe there's a confounding third factor, like smoking, where if you smoke, it reduces your cholesterol levels and increases your cancer risk. So Catan's insight was that maybe there's a way to take advantage of the fact that this gene, ApoE, is involved in cholesterol metabolism. Now, you probably have, we talked about ApoE being involved in Alzheimer's disease. It turns out it's also involved in cholesterol metabolism, and in fact, that may be part of the mechanism by which it affects risk of Alzheimer's disease. So what might you do? How might you take advantage of this insight to try to disentangle the causation? Exactly. So the idea is, let's look at different genetic variants, people with different genetic variants of ApoE, and look at their cancer risk. So the idea is that if you have the variant of ApoE that reduces your cholesterol, then if cholesterol has a causal effect on cancer risk, then having the variant of ApoE that reduces cholesterol should, people with that variant should have higher cancer risk. So that's the basic idea underlying Mendelian randomization. The term didn't come until a few years later. And then there was an influential early review of the literature by George Davey Smith and Ibrahim that kind of summarized the evidence up until then and helped to make the field a coherent area of work. So the basic idea then is going to be to have a variable like in this genetic variant, in the case of Mendelian randomization, which we're using not because we're interested per se in the effects of the genetics, but as instrumentally. We call it an instrumental variable. We're using it instrumentally to learn about the causal effect of an exposure on an outcome. In this case, cholesterol and cancer risk. Okay, so the idea that we could use genetics essentially to create randomized experiments goes back a long way. There's a quote from Fisher saying that the different genotypes possible from the same mating have been beautifully randomized by the meiotic process. A more perfect control of conditions is scarcely possible than that of different genotypes appearing in the same litter. But this is exactly the idea that Alex was just talking about in the context of using this natural experiment in order to learn about the effects of genes. And here we're going to use it for the somewhat different purpose of learning about the effect of some exposure on an outcome. So here is a nice figure that makes an analogy with randomized controlled trials. So in a randomized controlled trial, you have some randomization that you, the researcher, conduct. You have a treatment condition and a control condition. And by randomizing, you equalize the confounders across conditions. And the comparison between outcomes gives you the effect of the intervention. The idea of Mendelian randomization is that we use the natural experiment of random segregation of alleles. That creates a treatment group, people with higher levels of cholesterol, and a control group of people with lower levels of cholesterol. Because it's a natural experiment, we've also equalized confounders between the groups, and we compare the outcomes. So this is a figure that shows the use of instrumental variables in general in gray, and Mendelian randomization studies in particular in black, in the medical literature over time. Clearly there's been substantial growth over time. This only goes up to 2015 because it was a review paper then. I think the growth has continued since then, and so now there's many of these papers. It's really a very hot area within epidemiology in general. And one thing I want to highlight is that the growth really took off starting around here with the Gwas era. And I'm going to talk later about the way that Gwas studies have been exploited for Mendelian randomization. OK, so I'm going to first give the background on instrumental variables, which is the general method of which Mendelian randomization is a special case. Then talk about classical Mendelian randomization, by which I mean Mendelian randomization with a single genetic variant. Then I'll talk about how Mendelian randomization has been developed in with the advent of Gwas. Very briefly mention some other uses of Mendelian randomization besides causal inference that you may come across, and then just end with my own reflections on the method and the literature. OK, so early on in the Mendelian randomization work, it was recognized that it's a particular case of instrumental variables, and there's been a lot of there was substantial rapid progress then of borrowing ideas from instrumental variables into Mendelian randomization because there had been many years of developing instrumental variables in economics. It was instrumental variables was first described by Philip Wright in 1928. It's actually a very interesting origin story. Philip Wright is the father of Sewell Wright, who is a famous statistician and geneticist. And there's been some controversy about whether the true inventor of IV might have been Sewell Wright rather than his father. But there's been some clever sleuthing using writing styles that I think convincingly shows that it really was the father, the economist Philip Wright, who developed it. But interestingly, the derivation in the original paper, there were two derivations. One, an algebraic derivation, typical of an economist. And then there was a path diagram derivation. And it seems likely that the path diagram derivation was the result of the influence of Sewell. OK, so now this instrumental variables has been used widely in a lot of different disciplines. So the idea is we want to estimate the causal effect of an exposure, E, on an outcome, Y. So we have a causal equation of interest. And the basic problem is that if our exposure is correlated with the error term, either due to reverse causation or third factor confounders, then we're going to have a biased estimate if we just try to run an OLS regression of the outcome on the exposure. So that is typically called omitted variables bias. I think that's that name of the bias suggests that the way you would solve it is by controlling for more stuff, the omitted variables. And that was, for decades in economics and other disciplines, the standard way that you would try to deal with this kind of problem, just control for more things. The problem is it's hard to know when you've succeeded. This is what Patrick referred to as the plugging the dikes problem. If you're clever enough to think of another problem, then you need to control for something else. There's another issue that actually also comes up when you try to run an OLS regression, another kind of bias that's going to come up later in the talk, so I'll mention it here, and that is that if the exposure is measured with error, then even if you don't have this omitted variables bias, you're going to get the wrong beta estimate. There's going to be an attenuation bias, or in multivariate settings, an errors in variables bias. More generally, that Patrick talked about that when he talked about polygenic indexes and talked about the measurement error correction for polygenic indexes. OK, so instrumental variables is actually going to deal with both of these, as we'll see. So the idea is that we can get a consistent estimator of beta if we bring in another variable, instrumental variable x, that affects the exposure E. So we have another equation that the instrument affects the exposure. And it has to satisfy the usual assumption that the instrument is uncorrelated with the error term in this equation. And then the two additional assumptions, which are really the key assumptions for instrumental variables. The first is the relevance assumption, which is that this coefficient has to be non-zero. It actually has to, the instrument has to actually matter for the exposure. And in fact, saying it this way is a little bit, it's not just that it has to be non-zero, as we'll see. It actually has to be strong enough. So we'll come back to that point. And the other assumption is the exclusion restriction, what economists call the exclusion restriction. It goes by other names in other disciplines. Formally, what that means is that the instrument is uncorrelated with the error in this equation. That way of phrasing it isn't entirely intuitive. I think a clearer interpretation is actually the assumption that conditional on the exposure, the instrument is independent of the outcome. So if you have a randomly assigned instrument, that's going to be satisfied. But more generally, it has to be that the instrument isn't somehow affecting the outcome in some other way other than through the exposure. That's the idea. This assumption actually implies this covariance condition, but is slightly stronger. So under these assumptions, so just going back to the Catan example, the point here would be, relevance would be ApoE matters for cholesterol levels, and exclusion restriction would be ApoE only matters for cancer risk by affecting cholesterol levels. There's no other reason why it would be correlated with cancer risk. OK, so there are a number of instrumental variables estimators. I'm going to focus on the simplest one, which is also the one most relevant for most Mendelian randomization applications, and that's called two-stage least squares. And this is the two-stage least squares estimator. It's the ratio of the estimated covariance of the outcome and the instrument to the covariance, the estimated covariance of the outcome with the exposure. And that's a consistent estimator for the true causal effect beta. So I'm going to give you a heuristic derivation of this estimator. In the problem set question, you give a more formal proof where you actually do the two stages of least squares that give it the name here. I'm going to, well, actually, first I want to show you the assumptions in a path diagram representation. So the relevance assumption is that the genetic variant affects an exposure. In principle, there's this confounder that could affect both the exposure and the outcome. And also, in principle, the outcome could affect the exposure. But we're going to bring in this variable of the genetic variant. And then the exclusion restriction says that the genetic variant doesn't matter for the outcome in any way other than through the exposure. So in particular, it doesn't matter. There's no effect of the genetic variant on the confounders, or no correlation, and no correlation between the genetic variant and the outcome in any other way. The reason, now, in the path diagram, these are kind of two different, kind of two assumptions. And often in genetic epidemiology, you'll see it presented as two different assumptions with different names. OK, so here's a heuristic derivation of the two-stage least squares estimator. We can imagine, instead of, even though we're interested in the effect of the exposure on the outcome, we can imagine running a regression instead of the outcome on the instrument itself. So we call that the reduced form regression. And under our assumptions, that's going to give us a causal effect, because the instrument is the instrument is as good as randomly assigned. The problem is, so this is actually sufficient for drawing an inference about whether the exposure under our assumptions. It's sufficient for drawing an inference about whether the exposure matters for the outcome. Because if this is 0, then the exposure can't matter, since we know that the instrument affects the exposure. And if this is non-zero, because we know by assumption that the instrument works through the exposure, then it must be that there's a non-zero effect of the exposure. But it's giving us the answer in the wrong units. It's telling us the effect of a 1-unit change in the instrument, and what we want is the effect of a 1-unit change in the exposure. So we supplement this regression with another regression, which in the 2 stages of two-stage least squares corresponds to the first stage. And that's the regression of the exposure on the instrument. So that also gives us a causal effect. And in order to then get what we want, which is the effect of the exposure on the outcome, we rescale the causal effect from the reduced form regression using this regression coefficient. In particular, we divide the reduced form regression coefficient by the first stage regression coefficient. And that tells us, that puts us in the units of a 1-unit change in the exposure. OK? And the variances of x cancel, so we just get the ratio of the covariances from those 2 regressions. So I think this is a very helpful way of thinking about what's going on with instrumental variables regression. And actually, both of these ways of expressing it are going to be useful in what we say later. OK, so here's an example, an early example from the economics literature of instrumental variables that helped usher in a period of time in economics when, it seemed like every important empirical paper was an application of instrumental variables regression. This was a paper from 1990 by Josh Angrist, and actually it was referenced, I think, by Dalton, or at least the instrument was. The idea here was to look at the effect of veteran status on earnings. And there had been, economists have, run lots of regressions of earnings on things, and the question, there was a coefficient on whether you're a veteran. It's correlated with your earnings, and the question is, is that a causal effect? And Angrist's idea was to use the fact that there was a draft lottery for the Vietnam conscription as an instrument for whether you ended up serving in the military and thus becoming a veteran. So indeed, this instrument is relevant. This lottery outcome, whether your birthday was drawn, affected where you were in the list of who got called up when, in what order people got called up for military service, depending on how many people were needed. So it affected the probability of serving in the military. And the exclusion restriction is satisfied because here the lottery is actually random. And so it's independent of everything, including your earnings. And the bottom line of the paper is that the earnings of the veterans, the white veterans, were about 15% less than the earnings of non-veterans. So serving in the military reduced income. So this was a very convincing application of instrumental variables. There have been as I mentioned, lots of applications in the economics literature. This is a review from 2001, which was maybe the high point of use of instrumental variables in economics, and looking back on lots of papers in the 1990s. A lot of the work, is extremely clever. And the art of doing this kind of empirical work, a lot of the art was coming up with the good instrument. So for example, If you wanted to look at the effect of fertility on education or on labor supply, you could use whether people had twins. Because whether you have a twin or not is random, and if you have a twin, you end up with an additional kid. So you can see whether the number of kids affects things like your, whatever outcome you want to study. If you want to study the effect of getting treatment for a heart attack, like getting surgery when you have a heart attack on your later health, you could use proximity to a cardiac care center, because people who are closer are the ambulance is going to take them to get the surgery, and if you're too far away, then they won't. So these are the kinds of things. Patrick mentioned the school leaving, the change in the compulsory schooling age in the UK. Compulsory schooling age laws have been an instrument that a lot of people have used to look at the effects of education, because when a law is passed, that affects how much education you get, and then you can use that to look at the effect on other things. OK, so now I want to make some remarks about instrumental variables. So first of all, in some cases, it's not credible. Just the instrument by itself without control variables is not going to satisfy the assumptions. So for example, your distance to a cardiac care center, you would worry that people who are in higher socioeconomic status areas are going to have hospitals, care centers that are closer to them potentially, and also they're going to have better health for other reasons. So you would want to be careful to control for things like your socioeconomic status or which zip code you're in or something like that, in order, maybe conditional on that, distance to a cardiac care center is unrelated to, or satisfies the exclusion restriction. So the derivation we gave before and all the logic all goes through conditional and control variables. So if the assumptions hold conditional and controls, then if you run the regressions conditional and controls, you can apply the method. Also, you might want to use controls to improve precision, just like with OLS, and as Patrick talked about in the lecture on polygenic indexes. OK, now I previewed this before. One very nice feature of IV regression is that it automatically corrects for measurement error when you're estimating the effect of the exposure on the outcome. And I think one way to see it immediately is that in the two-stage least squares estimator, you're taking a ratio of covariances. The reason you get attenuation bias in a standard OLS regression is that you're taking a covariance divided by a variance, and that variance of the exposure includes measurement error. But in the covariance, measurement error, the covariance is this, bilinear operator, so the measurement error, if it's classical, it's just uncorrelated with the other stuff, it goes away in the covariance. And in fact, in economics, sometimes IV regression is used mainly to get rid of measurement. It's not used to try to get a causal effect. It's just used to get rid of measurement error. So another comment is that two-stage least squares doesn't require that you have all the data in the same data set. You could do what's called two-sample instrumental variables, where you run the reduced form regression in one data set and the first stage regression in the other data set, and you take the ratio of the coefficients. And that works because we could think of the two-stage least squares estimator as this ratio of coefficients from two different regressions, and there's no reason these two regressions could be run in different data sets. And that's going to be important. We're going to when we come back to the use of Mendelian randomization in Gwas, from Gwas. OK, so the last comment is that we've been talking about a linear model, and that's all I'm going to talk about to keep things simple. But if, more generally, we are dealing with a nonlinear model, then what you're getting from IV regression is a local average treatment effect. So the reason that's not relevant in the case of a linear model is that by assumption in a linear model, the effects are the same for everybody. But if you have a nonlinear model, treatment effects are going to be different for different people. And in particular, what you're getting in instrumental variables regression is an estimate of the causal effect local to the subsample for which the instrument affects the exposure. So, for example, in Patrick's application of the compulsory schooling, the increase in the compulsory schooling age from 15 to 16, he's estimating the effect of an additional year of education for the people who were affected by the law. So he's estimating the effect of going from age 15 to 16, or 15 to 16 years of being in school from age 15 to 16, not the effect of additional year of education for people who are 20. And that's, by the way, why he made the comment about being low-powered even despite using the UK Biobank with hundreds of thousands of people, because effectively he's only getting variation from the people who are either staying an extra year of school because of the change in the compulsory schooling age. So this can also matter for Mendelian randomization. So if we use a genetic variant for educational attainment, some genetic variants might matter for your high school completion. A different genetic variant might matter for your college completion. And those are potentially going to give you different causal effects. OK, so the reason why instrumental variables is so, hopefully I've just convinced you it's extremely powerful and very cool. But the reason why you have to be so careful with it is that if its assumptions are violated, it can do very badly. And its assumptions can be violated in ways that are, you may not realize, because the exclusion restriction is untestable in your own data. So in particular, if the exclusion restriction is violated, then the estimator is not consistent. And the way to see that is, the numerator is the causal effect of the instrument on the outcome from the reduced form. If the exclusion restriction is violated, if the instrument matters for the outcome in some other way, this is not going to be giving you the causal effect of the instrument. So rescaling it is not going to give you the right effect of the exposure on the outcome. And even small violations of the exclusion restriction can lead to severe bias. The other assumption was this relevance assumption. And I warned you that it really is, you need that the instrument matters enough for the exposure. And in particular, what matters is the F statistic for the regression of the exposure on the instrument. So the way to think about that is it's essentially about the variance that you're explaining in the exposure adjusted for the number of degrees of freedom. So if you have lots of instruments, that counts against you. The way to think about why that matters is that if you have a low F statistic, then this denominator is going to be noisily estimated. And if that, that can matter, that can really affect what you're getting, both in terms of the variation of your estimate, but also, the expectation of this thing. In order for the expectation to be the right expectation, you need the denominator to be estimated pretty well.
Is that because it's also going to be close to zero?
Yeah, well, if it's a weak instrument, yeah, then exactly, then it's close to zero in the relevant sense, and so the thing also, it blows up. Exactly, yeah. Yeah.
And what really kills you, right, is that the error in the denominator is also correlated with the error in the numerator, right? Because generally, when you see weak instruments, that it's biased towards the OLS estimate. And I think that's just due to the fact that there's a lot of error in the numerator and denominator, and they're correlated in the same way that the OLS estimate is.
Right.
Yeah. OK, good. So yes, it also weak instruments magnifies the bias from violation of the exclusion restriction. And there's recently been some developments that don't seem to have been taken on board yet in Mendelian randomization. So if you're working on Mendelian randomization, you should look into this literature on weak instrument robust inference, which is about how to do, how to get better estimators that adjust for the weakness of the instrument. Now it's going to end up expanding your confidence intervals quite a bit, but it's the right thing to do.
But isn't it necessarily, the standard one is necessarily biased, right? It's biased.
It is biased,
consistent,
exactly.
yeah.
It's biased but consistent.
Is there not a bias? Is that recent thing like a bias correction?
Yeah, it's essentially a bias correction, but also getting this and also getting the standard errors right. Okay, so now we're going to talk about the application to Mendelian randomization. So I'm going to show you, start with an example. This is a nice application that was done using the China Kadoorie Biobank. It was published in 2019. So the background for this paper is that there's a lot of work in epidemiology looking at the relationship between alcohol consumption and cardiovascular risk. And you've probably read that things like, drinking a little bit of red wine is good for you. It's a lot of drinking that's bad for you. And so that comes from this kind of correlational evidence, which tends to find that a little bit of consumption of alcohol is associated with a reduced cardiovascular risk, but then increased cardiovascular risk when you drink a lot. So the question in this paper is, what is the causal effect of alcohol consumption on cardiovascular risk? So they looked at about 160,000 individuals in the China Kadoorie Biobank. Here are the exposure variables alcohol intake. Now, just to be totally clear about the red wine thing, Chinese people don't drink a lot of red wine. So this evidence is actually mostly about the effect of spirits consumption. But if you think that it's operating through alcohol, the results should generalize. The instruments here are two genetic variants, both related to the to alcohol dehydrogenase genes. So one of these variants is involved in the breakdown of acetaldehyde. So this is a variant that is, basically there's no variation among Europeans, European ancestry people. But in Asian ancestry people, there is this loss of function variant here that basically prevents the breakdown of alcohol. And it's what causes a lot of people of Asian ancestry to turn red in the face when they drink even a little bit of alcohol, and it's very uncomfortable. So the idea is to use this variant as a, people who have the version of that variant will not drink alcohol because it makes them very uncomfortable. And then they also use another variant, less important one, but also involved in alcohol metabolism. And their outcome variable, they use a number of outcome variables related to vascular disease. And one nice thing about this paper is they use as a negative control group Chinese women who don't drink a lot of alcohol. So the variation is going to be in the men. And what is having this negative control group, can you anticipate how that might be useful to have a group that doesn't drink alcohol? Yeah?
Because we're not going to observe this variation that we will observe in the men, meaning that the men with this allele will have reduced or increased vascular problems, whether there will be no association with women.
But what if we do find an association in women between genotype and vascular disease?
Then we can't rule out confounding.
Exactly. So it's a nice check on the exclusion restriction. It's not a test of the exclusion restriction because exclusion restriction is always untestable, but it's a nice check because if the exclusion restriction is if the exclusion restriction holds, then we should not see an effect on Chinese women. If the exclusion restriction, we might not see an effect on women, and exclusion restriction could still be violated in some other way. So that's why it's not a test. But it gives us some comfort. OK, so here's the bottom main results. And I don't want to spend a lot of time walking through this. I'll just try to give you a quick sense of what this is showing. The top, and this is 3 of the outcomes that they looked at. So this is stroke, hemorrhage, or this is ischemic stroke, intracerebral hemorrhage, and total stroke. And the top 3 panels are showing the observational data, and the bottom 3 are showing the causal evidence from the Mendelian randomization study. So what you see in the top is a replication of what you usually see in the correlational data. So the people who are ex-drinkers or non-drinkers have high risk of these bad outcomes, and then they're lower risk if they drink a little bit, and then risk is increasing with the amount that they drink. So this drop here, which is the part that is maybe surprising, but there's always been worry that maybe that could be due to confounding, like sicker people, or are the ones who don't drink. And indeed, what they find when they go to the Mendelian randomization evidence is no longer this non-monotonicity. Now, the people who don't drink very much, the less you drink, the lower your risk. This is for men. Here's confirming what they thought going into is that there's a difference on average between men and women's consumption, with the women drinking very little. These different groups, these are basically genotype groups across the two different variants. And then this is a table comparing men and women. So I just want to focus your attention on these 2 rows. This row here is showing the effects for men and women for each of the 6 outcomes they look at. So for example, for systolic blood pressure, there's this effect estimate and this confidence interval that's non-zero for men. For women, it's close to 0, and the confidence interval includes 0, or almost includes 0. And you see that for each of the outcomes. And then here's a test of the difference between men and women, which in all cases is, or almost all cases except for the last one, is very small. OK, so that's example 1 of Mendelian randomization. Yeah?
Sorry, I'm just worried. So it seems to me, I think this variant, it could be present in different proportions in different regions of China. I mean, China is huge. It's not like a monolith.
Yeah.
It could also be correlated with like local drinking habits, and mostly we're about northern, southern China. So I'm just worried that this instrument is just picking.
Yeah, that's a good point. So they try to be careful about that. They're aware of regional differences, and actually all of the analysis is done within region, and then they meta-analyze their estimates. But I think that I think the kind of issue you're raising is exactly the kind of thing that always comes up in these studies. There's something you can worry about, and then maybe they can deal with it. And the question is, have they dealt with enough of those things that you're convinced? OK, so here's another example. The background for this paper is that more smoking is associated with higher stress. And yet, people anecdotally say that they smoke to reduce stress. There's different directions of causation or causal pathways you can imagine here. So to try to get at whether more smoking causes higher stress, these authors looked at about 90,000 individuals in Copenhagen. The exposure variable was amount of smoking. The instrument was a Snip that has. It's the single Snip with by far the strongest association with amount of smoking. It's in a nicotinic acetylcholine receptor gene that metabolizes nicotine. It's the biology of this gene is very well understood, how it relates to smoking metabolism. So then their outcome variables are various measures of psychological distress. And they use as a positive control group another outcome. So in this case, the control group is not another group of individuals. It's an outcome variable. And here it's lung function. So how is it helpful to have another variable, lung function, as another outcome variable?
You
Yeah.
can rule out pleiotropy?
How?
If there's no association with lung function, but there is with smoking.
Do you think there would be no association between this variant and lung function?
I don't know.
What would you hypothesize about the relationship between this variant and lung function? What would you expect? Yeah.
It'd be negatively associated because the people would be more likely to be smokers.
Right. If it affects smoking, we expect it to reduce lung function. So that's the idea here, that if they find no effect of, in this case, if they find no effect of the instrument on stress, then it's comforting for that to see that there is an effect on lung function, because that's one you would expect to see. So in fact, that's what they find. So here's the observational evidence on lung function. So this is showing people in these different never smokers, former smokers, and then people who smoke increasing amounts of cigarettes. And this is the relative risk of having problems with lung function. So as you'd expect, more smoking is associated with worse lung function. Here's the observational association with stress. That's what was in the prior literature, that people who smoke more have more likely to experience stress. Here are the reduced form associations. So this is now from just the reduced form regression. There's no need to go the full two-stage least squares here, because we're just asking whether there's an effect or not an effect. And in particular here, we're finding no effect. So you can just see that in the reduced form, looking at the effect of the genotype on the outcome. So here, there is an effect on lung function of genotype, but no detectable effect on stress. And the confidence intervals are, I think, fairly small relative to what the effect sizes in the observational data. So at least no big effects on stress. OK, so now I want to talk about, we talked about this a little bit already in some of the back and forth. I want to talk more carefully about the threats to the assumptions in Mendelian, the threats to the instrumental variables assumptions in the context of Mendelian randomization. So what kinds of things could lead to violations of the exclusion restriction when our instruments are genetic variants? Pleiotropy. Good, that's a big one. And in fact, pleiotropy, there's a lot of evidence of pleiotropy for a lot of different phenotypes. And for complex phenotypes, you almost have to have pleiotropy, because a variant is going to affect something like educational attainment through some mechanism, through affecting your personality or some cognitive abilities or something. And whatever mechanism that is, we know that matters for other stuff. OK, what else? The variant may not be randomly assigned. And what kind of problems is that going to cause? OK, yeah. Exactly. So gene-environment correlation and the subtypes of that. So population stratification, indirect effects. Those are reasons why the exclusion restriction could be violated. Pleiotropy. So I just showed the answer. And then here's the other one. So LD. And this is really a killer, because even if you can be sure that some genetic variant doesn't have a pleiotropic effect, you really know what its function is, and you've ruled out gene-environment correlation, maybe with a within-family study, it could be an LD with some other variant that has an effect that ends up influencing the outcome, or Yeah, that's or has some gene environment correlation if it's not within family. It's not a within family study. How about weak instruments? Why might that be a concern here? Cyan.
Smaller power.
Small effect sizes, exactly. So for complex phenotypes, we worry about small genetic effect sizes. Okay, so the ideal scenario is you could ensure. How can you ensure the exclusion restriction holds? How can you rule out gene environment correlation? So I think you're suggesting controlling for the relevant environmental variables.
Yeah, I was just thinking like I would just want to look at like.
Sure, you could look at whether environmental variables that you've measured are correlated with genotype, but what if they're not? Can you be confident that you've ruled out gene environment correlation? No, because there could be unmeasured things. So what can you do to be? I mean, to be. What's the best you're going to do at ruling out gene environment correlation? Yeah.
Understanding the biology of the gene?
Yeah, so understanding the biology is very helpful with the exclusion restriction, because if you know that the genetic variant matters through a particular mechanism that's relevant for the exposure but not for the outcome, that can give you confidence. But you might still be worried about gene environment correlation. So how can you rule out that concern, or mostly rule out that concern? Yeah.
You need a really good control group.
Control group is definitely helpful. Well, maybe this is too easy of a question. Yeah.
Estimating principal components analysis.
Principal components is good. I'll give you a hint. We had 2 lectures on this idea. Cyan. Yeah, control for parental genotypes. Exactly. So exactly, impute them and control for them. So there's actually a paper that advocates this, not the imputation part. They talk about the sibling fixed effects, but we'll forgive them. They advocate this is something that should be done going forward as GWAS samples with family data become more available. Everyone should adopt this as best practice. And then this is Tanner's idea. Use a genetic variant with a known biological function that's directly related to the exposure. Now, you also ideally would have strong reason to believe that not only the genetic variant, but also all the variants in LD with it are unrelated to the outcome. Okay, so this is the ideal. And then someone else mentioned also having a positive or negative control group for the causal effect estimates can give you further confidence, like we saw these in these examples. How about avoiding weak instruments? What kind of genetic variants would you want to focus on? Well, yeah, ones with relatively large. So ApoE is a great one. I mean, it's all really, it's not just about the effect size, though. It's also about the relative to the size of the sample. So you need to have this large enough F statistic. So things like ApoE, or the less good is that nicotinic acetylcholine receptor variant. But that's better than a genetic variant associated with educational attainment for a given sample size, because those are that's the ordering of the effect sizes. What we need is a large effect of the genetic variant on the exposure relative to the sample size that we're using for the study. Okay, so this is the ideal. There's never been a Mendelian randomization study satisfying these ideal conditions. And in particular, controlling for parental genotypes has almost never been done. But I think this is what you should have in mind when you're evaluating a study. Have the concerns in mind, have this kind of ideal scenario in mind, and try to think about how well the study stacks up against this ideal, and it could be more or less persuasive. Okay, so now we're gonna
Sorry, so you showed us kind of conveniently these candidate gene examples. So when you have many SNPs potentially that influence the outcome, doesn't that make the weak instrument issue much worse?
Potentially, yes, but we're going to talk about that in just a moment. So hold that thought. We're now going to talk about Mendelian randomization with Gwas summary statistics. So in the economics literature, there's a long tradition of doing instrumental variables with multiple instruments. And in economics, the motivation was concern about the exclusion restriction. So the idea was to test the null hypothesis that the exclusion restriction holds. As you might see the name, the Sargan over-identification test. That's what people talk about. And the basic idea is that if the exclusion restriction holds for all of your instruments, then if you do the IV with different instruments, you should get the same estimate. So we're going to test whether we're getting the same estimate using different instruments. Now, over the years, it's been realized that there are some major problems with this. So I'll tell you 3 of them. One is that you often lack power to test this hypothesis because the hypothesis is about the difference in effect sizes. So that means that the uncertainty in both of your estimates matters. Second problem is that even if the null hypothesis is actually true, the exclusion restriction could still be violated because it could be that all of your estimates are biased. So you get the same answer, but they're all biased in the exclusion restriction in the same way. A third problem is that the null hypothesis can be true even if the exclusion restriction holds. And that's because the instruments can be estimating different local average treatment effects. So if the effect on high school completion is different than the effect on college completion, you might get different estimates and so reject this null and say, oh, my exclusion restriction fails, but they might have been perfectly valid instruments giving you different local estimates. Okay, so it's not clear. So what economists have concluded from all this is we could do this, but it's not clear what we learn in the end. And so I think that the approach in economics these days, or the common view in economics, is rather than using multiple instruments to try to test this, let's just try to focus on the instrument or small number of instruments that we think are really the compelling ones and are going to give us good local average treatment effects. OK, so now in the Mendelian randomization context, there's been a somewhat different motivation and approach to doing multiple instruments. So one of the major reasons why there was relatively little Mendelian randomization work in the early 2000s was that there just weren't a lot of genetic associations to use as good instruments. And the success of Gwas studies in identifying lots of variants solved that problem, because now there's lots of potential instruments that you could use. But the exclusion restriction is pretty likely to be violated for any particular SNP that you find in a Gwas. So the goal in the Mendelian randomization literature has been to use multiple instruments to try to relax the exclusion restriction to some weaker assumption that you think might be more likely to hold. It's still going to be untestable, but at least it's weaker. There are many examples, and I've just put some of the ones that you might have been most likely to hear about on this slide, and I'm not going to go through all of these. But I guess let me mention a couple that are going to come up. So as we'll talk about in a moment, in the Gwas literature, all of these studies use the two-sample IV, two-sample Mendelian randomization. And to use the multiple summary statistics, they typically do, to use them most efficiently, they do a kind of inverse variance weighted approach. So that maximizes power. That assumes that all the instruments satisfy the exclusion restriction. MR-Agar regression is on the problem set. And so you'll work through the idea there. That's a pretty popular method. And the assumption in MR-Agar is that each of the instruments can violate the exclusion restriction, but the extent to which the exclusion restriction is violated is uncorrelated with the strength of the instrument, the relationship between the instrument and the exposure. There's also a median-based method that basically assumes that, the exclusion restriction might be violated for lots of your instruments, but for at least half of them, it holds. Okay, so that's the flavor. It gives you some flavor of the kinds of approaches that there are. No, I actually mentioned one more. MR-Presso is a method that basically does MR-Agar, but first looks for heterogeneity in the effects, and if there are outliers in terms of the causal effects, you throw away those instruments, and you focus on the ones that are giving you more similar effect estimates. OK. So let me give you an example of this kind of study. So this is a paper. The background for this paper is that education is correlated with heart disease and also lots of other health outcomes. So this paper wanted to answer the question, does education cause reduced risk of heart disease? So the exposure variable is educational attainment. They're going to do 2-sample IV, which means they're going to use estimates of the effective genetic variance on educational attainment for the reduced form. For the first stage. That's going to come from EA2. So they use the 162 genome-wide significant SNPs from EA2. And remember that for this 2-stage approach, you're taking the ratio of regression coefficients. So you're just using the GWAS summary statistics from 2 different GWASs. This one is the effect of the SNPs on the exposure. And then we're going to take another GWAS, which was a GWAS of heart disease. And that gives you the effect of the genetic variance on the outcome. That's the reduced form. And then we're going to divide those coefficients for the 162 where we have our instruments. So we're going to look up these 162 SNPs, or if they're not available, use SNPs that are in high LD with them in the GWAS for coronary heart disease. And then they use one of these methods, which is bidirectional MR. So they say, we can just as easily look at instead of just looking at the effect of education on heart disease, we can also look at the effect of heart disease on educational attainment by just looking up the top hits in this GWAS in educational attainment and dividing those coefficients. So what they find is evidence for a causal effect of educational and coronary heart disease, but not an effect of coronary heart disease on educational attainment. So here's the estimates. Maybe I won't spend time going through this. I'll just show you. These are the observational estimates, just the raw correlations in other data between educational attainment and coronary heart disease. And these are the Mendelian randomization estimates using the 2 sets of GWAS results. And they do it. This is pretty common in these papers. They use different methods. So they show that they're getting similar estimates whether they do conventional inverse variance weighted Mendelian randomization or MR-Agar or this median-based Mendelian randomization. The estimates all look pretty similar to each other and pretty similar to the observational correlations. And then here's the effect for the other direction, the effect of coronary heart disease on education. And here the estimates are all pretty close to 0. OK, so here's my assessment of this approach. I mean, I think it's like Mendelian randomization in general, it's potentially valuable. This is a powerful method, and the extensions in this GWAS literature have demonstrated that having multiple instruments can provide useful additional evidence. But there are some concerns that come up, especially in this context where you're using multiple instruments from GWAS that we should worry about. So one is that a lot of these methods assume that all the instruments are estimating the same local average treatment effect. But there's no reason in general for that assumption to hold. It's not clear how to interpret the results if it doesn't hold. Another concern is that this comes back to the question about weak instruments. in general, using lots of instruments would potentially create a weak instruments problem in a lot of contexts because it's about the F statistic and you're increasing the number of degrees of freedom. But here, that's actually not such an issue because they're focused on genome-wide significant SNPs. And so these have such low p-values that the F statistics are huge. So it's very unlikely that these studies have a weak instruments problem. But they have another problem, which is the winner's curse problem that Patrick talked about a number of lectures ago. We're focusing on the most significant hits. So we're getting biased estimates in the in the reduced form, sorry, in the first stage regression estimates. And so that's going to lead to systematic bias in the results that come out of these papers. It's very unusual to see an adjustment for winner's curse in these kinds of papers. And finally, and maybe most fundamentally, what makes these approaches appealing is that they don't have to rely on the exclusion restriction. They weaken the exclusion restriction. But the problem is it's hard to assess the assumption that is replacing the exclusion restriction. So what often happens in these papers is that instead of trying to defend the assumption, what the papers do is report different kinds of analysis relying on different weakenings of the exclusion restriction. And that's nice. I mean, in general, when you have conclusions that make different assumptions that are convergent, that gives you more confidence in the conclusion. But this is my assessment. I personally, and this is also probably my bias as an economist, I am usually more persuaded by a single instrument that is well justified than by lots of instruments that probably many of which violate the exclusion restriction in ways that I don't understand. Okay, so that was my controversial slide. I should be clear. I mean, this is not a consensus view. There's actually a lot of enthusiasm. A lot of people are very enthusiastic about GWAS-based Mendelian randomization, and a lot of GWAS studies report Mendelian randomization results just as something that they do. We've actually been pretty careful to avoid including Mendelian randomization in our GWAS of educational attainment that we've done because we are very worried about violations of the exclusion restriction and whether the results would mean anything. But I think this is a minority view.
Okay, can I
Yeah.
make a few comments? So I think so I don't use.
Do you want to unmute are you on the?
Oh, I'm not.
Patrick, do you mind passing just so that the people can hear? Okay.
So yeah, I don't use MR myself, but and maybe Patrick, you know this. I had done some simulations a little while ago, and from what I can remember, I think that when you have one sample MR, then the winner's curse cancels out in the first and second stage. But when it's two sample MR, then it doesn't, and then the only way to deal with winner's curse would be to have an outside discovery sample for selecting your instruments. Or selecting based on biology.
It's not clear to me why it would cancel out.
Because the estimation error is correlated in the first.
Well, it's certainly going to be worse than in two sample MR because when you look up the results, for example, for the EA summary statistics and the coronary heart disease results, there's no winner's curse in the estimates in the coronary heart disease case, but there are in the educational attainment case.
But the error is going to be correlated in the observational correlation direction, right? So it's going to be biased.
I'm not talking about the error term. I'm talking about the estimation error that leads to winner's curse.
Well, yeah. So that's what I'm saying. So winner's curse is just systematic error, and you're saying that because that systematic error is correlated in the numerator and denominator, it would sort of cancel out, right?
Yeah, I think that's what I mean. I have just a fuzzy memory of doing this, so I actually just pulled up my script and I didn't want to run it right from there, but and I didn't annotate it well. But my memory was that when there was one sample, it wasn't anywhere nearly as much of an issue, if at all.
I just think it would be biased towards the OLS, and so it might be depending on where the OLS lives relative to the causal effect. It might look less bad.
Yeah. But yeah, and then to the second point, the way around it is just to choose your instruments not based on the same sample you're drawing your estimates from. Right? That's the traditional solution to Winner's curse in polygenic scores as well, right?
It's also the traditional approach to choosing instruments, prior to this use of GWAS, or you pick an instrument based on whether you thought that it was likely to satisfy the relevance and exclusion restriction assumptions, not because you did you found an association in some sample.
Right. And then the other thing that I felt like I was missing something when you were saying how do you deal with gene environment correlation, and then you gave your answer, and then I think I realized where I was kind of misunderstanding. I think you were referring to how do you deal with passive gene environment correlation, and then the within family estimate is correct, is the way to deal with it. But that doesn't deal with what I think you would probably classify as pleiotropy, which is maybe the genetic variant confers you as to have a propensity towards some behavior and self-exposure that then has the error term become correlated with the instrument. And in that case, that's residual gene environment correlation. It's just a different type. It's what we would typically call like active gene environment correlation.
Exactly. So we would call that pleiotropy.
Right.
And in the literature, the Mendelian randomization literature, you often hear the words horizontal and vertical pleiotropy. That vertical pleiotropy is part of the same causal chain, and horizontal pleiotropy is when the same variant is affecting different phenotypes through different pathways. Okay, so now I'm going to just briefly have one slide on some alternative uses of Mendelian randomization that are not for causal inference that you may encounter. So just want to make you aware of them and the connections with what we've talked about. So one use is two uses here. One is prioritizing causal SNPs. So this is you often see methods like SMR, GSMR, and HIDE done as part of GWAS studies. And the goal is you take your set of hits and say which ones are most likely to be functional SNPs. So the basic idea of SMR is that within a locus of a whole bunch of correlated SNPs, and you don't know which one is the one that's truly causal, the causal SNP is more likely to have gene expression that's correlated with the phenotype. So what you do in SMR is you run a GWAS of your phenotype Y, and then you estimate an MR model where you look at the effect of, you use the SNP as an instrument for gene expression to look at the effect of gene expression on the outcome. So this is the EQTLs Andrea talked about. These are these expression quantitative trait loci. They tell you how much expression you're seeing of the SNP when you have, yeah. So there are GWAS of these EQTLs. So you look at how much the genotype is related to expression of that genotype, and then you can use the results from those GWAS to do this two-sample MR. And this approach does not rule out the possibility that the genetic variant has pleiotropic effects on both expression and the outcome. So it's not nailing causation here. But if you do find an effect here, the argument is it's unlikely to be driven by gene environment correlation. And it may be that there's some pleiotropic channel, but at least you should investigate further this particular SNP because it may be the one that's causal. And then HIDE is based on the idea that if you have a locus that's correlated with the SNP and you're wondering, is there a single causal SNP there or multiple causal SNPs? Well, if there were a single causal SNP, then you'd expect that you're going to estimate all of the same Mendelian randomization effects for all of the SNPs in the locus because all of them are going to have an effect due to their correlation with the causal SNP, and the only thing that's going to affect the regression coefficients is LD, and it's going to scale the numerator and the denominator in the LD estimator, the first stage and the reduced form, in the same way, so it'll cancel. And so you should see you should estimate homogeneous effect size. So you can do a test for homogeneity, and if you reject it, then you say that there's more than one causal SNP in this locus. But the other use of MR that you might see is a method that's called Giv regression. And so this is using polygenic indexes. So notice we didn't talk about using polygenic indexes to do Mendelian randomization. Any idea why people haven't done Mendelian randomization with polygenic indexes as the instrument? Yeah, exactly. Pleiotropy worries just seem much more severe when you have a polygenic index. So that's not what's proposed in this paper. The central idea in this paper is to correct for measurement error when you're looking for the effect of a PGI. So we talked about this, Patrick talked about this a bit when he talked about the alternative method of correcting for measurement error that assumes a specific level of SNP heritability and then analytically corrects the estimates. Here, you don't make any assumption about the SNP heritability. Instead, you split your GWAS sample, which reduces your power a lot. But once you have the split samples, then you can create different PGIs with uncorrelated measurement error and use one to instrument for the other. And as we talked about, instrumental variables corrects for measurement error. So it's it's an alternative approach to correcting for measurement error. And this paper does talk about doing causal inference. But the basic idea for how they talk about doing causal inference is controlling for PGIs that might correspond to potential genetic confounds. So it's not really, it's kind of the standard thing for dealing with potential problems with omitted variable bias, which is controlling for stuff. It's not the IV approach to that. OK, so let me just end with some overall reflections on this literature. So again, now I'm editorializing and giving my perspective as an economist. So in economics, so I think it's fair to say that economists as a clan have a jaded view of IV estimation. In the 1990s, we talked about this Angris paper that was one of the early ones. After that, in some other early papers, IV estimation became widespread. It was, favored, or all the top papers and empirical papers in economics were IV papers. In the 2000s, economists became increasingly aware of the limitations of IV. And in the last decade, its popularity has gone down. And economists have been increasingly turning to actually implementing randomized field experiments wherever possible. There are exceptions. So things like regression discontinuity that Patrick talked about remains a popular approach where it uses an instrumental variables method of estimating it. Those are generally considered relatively more credible. But the kind of classic instrumental variables, things like distance to a cardiac center, those are less popular in the top papers. And the reason is that economists now think that finding applications that compellingly satisfy the assumptions is pretty rare. And there are cases where even seemingly ideal instruments turn out to be problematic. There's a nice recent paper that looks at weather, which has been used a lot as an instrument for all sorts of things because it seems like a great instrument. But the problem is it actually affects lots of things. And so there's lots of channels by which the exclusion restriction can be violated. Now, I think you can defend the popularity of Mendelian randomization in epidemiology despite economists' views. So this is my being, favorably and pushed in a particular direction, maybe by my association with genetic epidemiologists. But I think you could make a good argument that there are some key differences in epidemiology, which is that unlike in economics, where basically field experiments weren't done until recently, but now economists have realized and maybe gotten the resources now to do them, and they're producing better evidence. RCTs were always a thing in epidemiology. I mean, they've always been the gold standard, and it's not like they're not being done because epidemiologists didn't think of them or didn't have the resources to do them. It's just that they can't be done in the cases of things like the effect of alcohol consumption on diseases later in life. And we actually need to give medical and public health advice on these important causal questions in epidemiology. So the alternative in epidemiology is, if the alternative is observational studies, which it often seems to be, I think you can argue Mendelian randomization is an improvement on that. So, now I'm not willing to go all the way to saying, therefore believe every MR study you see, but I think they have an important role to play. Okay, so here's my takeaways, big picture, things to remember. MR is not as good as a randomized experiment, but it can be valuable when an RCD wouldn't be feasible, especially. More instruments isn't necessarily better. I would urge you to prioritize quality of instruments over quantity. As we've talked about, it's most persuasive when the genetic variant has a strong effect through a well-understood biological mechanism. And I think that the kind of MR studies we should see, the Gwas is extremely valuable for providing fodder for Mendelian randomization studies, but I'm kind of old school in the MR studies I like. Like, I would like to see MR studies that justify the instrument through a thorough examination of the known biology and also the variants that it's in LD with. And I'd like to see, when there are MR papers, to see the evidence written up in a way that in a responsible way. I think the assumptions need to be stated up front and assessed as part of the paper. I think researchers should spell out clearly the plausible ways that those assumptions could be violated in the particular context of the study. We should be thinking creatively about using positive and negative controls to assess the assumptions. We should be correcting for biases like the winner's curse and state what biases we haven't corrected for, and be modest when we're drawing causal conclusions from the evidence and using causal language, because there are still assumptions that have to be satisfied in order for that language to be justified. Okay, that's it. So maybe if there's a quick question, you can do it now. Otherwise, we'll... Yeah, Alex.
What about disproof? A lot of this is about whether we can estimate a causal effect reliably, but what if you get a zero coefficient? Can you infer there's no causal effect to the exposure?
No. So the question is, if you get a zero coefficient, can you infer there's no causal effect? And you can't. And the reason is because it could be that there's a causal effect, but a bias that goes in the opposite direction and cancels it out.
Seems very unlikely, though, doesn't it?
I think it depends on the context.
I think with all of these, the lesson is with MR, it's about just nudging you in one direction or another, right? So if someone did an MR study and they got a zero, then I might think it's slightly more likely to not have an effect, but I don't think it's conclusively that.
And I'm not as persuaded as by a randomized experiment that got a zero effect.
Sure.
Yeah.
Really quickly go back to something you said. We're talking about weak instruments. You said that the SNPs that we use typically have small p-values, so you don't have a weak instrument problem. But it's not so small p-values don't necessarily mean a large proportion of the variation.
No, but they mean a large F statistic. So they tell you something about the variance explained relative to the sample size. They tell you pretty much exactly what you need to know, which is the F statistic. Yeah. Okay. Yeah.
Right. Your argument that we need to prioritize quality over quantity in terms of what kind of genes.
That's my opinion. Yes.
Yeah. But
yes.
To me, it sounds like we can't use instrumental variables. No, the exposures which tend to be more complicated, right?
Yeah, I think that it's going to be challenging to use Mendelian randomization in a lot of contexts. I think for complex phenotypes, if the exposure is a complex phenotype, Mendelian randomization may just not be as useful a tool. I mean, if you're looking at the effect of educational attainment, I'd rather you find a compulsory schooling, law change than use a GWAS of educational attainment. Now, if you're studying, but there's other complicated things like alcohol consumption or cigarette consumption, where maybe it's more plausible. Okay.